Hello, welcome to CS61B Discussion 1. My name is Anjali and today we're going to be going over Introduction to Java. First things first, let's get some announcements out of the way. Welcome to CS61B. This semester is unprecedented in being online, so there might be some growing pains and changes as we go through, but we hope it'll be as wonderful as previous semesters have been. Discussion and lab signups are open. Please sign up for a discussion and lab section even if you're not sure if you'll go, because we are trying to make sure that there are TAs at all the times where people show interest. There are no discussions this week considering it's already Wednesday. This is a video walkthrough only discussion, but starting next week there will be discussions held from Monday to Wednesday. There are, however, lab sections this week starting Wednesday, so please go so that you can get your computer set up for the class in general. Some more general things, please read our ED guidelines before you post on the class forum to make sure that everything follows the rules and your post doesn't get taken down, because I know how annoying that can be. And the pre-semester survey is out and due this Friday. Please fill it out. It helps us know what kind of issues the students you guys might be facing and what concerns you have about the course. Let's get started with some content review. The first thing that you have to know about Java is that almost all code has to be contained within functions, and all functions have to be contained within classes. So, here is an example of a class, which you will get very used to with time. This first line here is called the class declaration. Here it tells you the name of the class, in this case, CS61B student, the fact that it is a class, and some more information that we'll go over next week. Underneath that, these three lines are properties of the class, or variables. The top two are instance variables, which are only relevant to a specific instance of the class, or in this case, a specific student, versus some variables that are relevant to the entire class, or all instances in general. So, in this case, each individual student has their own ID number and their own grade in the class, while all students share Professor Hug as their professor. The next block of code we see here is our constructor. This is how we make new instances of our class. An example here is, you can think of CS61B student, the class, as a sort of mold of what a CS61B student is. For instance, all CS61B students have to have ID numbers. That's important. So that's part of the class. The constructor allows you to create each individual student, which is a unique instance of the class. In this case, you pass in an ID, which can be whatever you want, and it sets up students' ID number to the ID and their grade to the default initial grade, which is 100%. The next block of code, the next two blocks of code, are both functions. The first one is an instance method. This one is called watch lecture and is called on a single student, a single instance of the 61B student class. It doesn't really make sense as a concept to say 61B student went to class, right? You would say John, the 61B student, went to class. On the other hand, the second method, which is a class or static method, refers to all students. So this is what you would run if per se you wanted to update the grades across the entire class. This is not specific to any one student. This is just something that you can do to all students. You can kind of think of functions as actions and variables as properties. This doesn't completely hold true when you get to more abstract stuff, but for a simple idea of how a class works, it's good. Now, what can you actually do with classes? Well, before you can actually do anything with the class, you have to instantiate it. Instantiating a class is when you call the constructor, which we mentioned before, in order to create an instance of the class. There are 3 steps to instantiating a class. The first step is declaring the variable. In this case, CS61, this variable, student1, is of type CS61B student. You can imagine it as creating a box that's labeled student1 that can only contain CS61B students. The next line here is doing 2 things. Firstly, it's instantiating the class, which it's doing right here. The new keyword tells your computer to look for the constructor of the class. 61B student is the name of the class, and if you recall from earlier, our constructor had a parameter that was ID. So this is the ID number of our new student. So we are instantiating, and then we have to assign this instance of the class to our variable. We're taking our student and we're putting him in the box that he fits in. The reason I put these together, even though they're technically 2 different steps, is that if you instantiate a student and you don't assign him or her, the student will just cease to exist. You'll never be able to access that instance of the class ever again. So you have to assign when you instantiate, but declaration can be done on a different line. This third line is just an example of where all 3 are done at once. So this section over here is declaring the variable. This section over here is instantiating another student. And then the equal sign assigns that instance to the variable. The next thing is that, like I mentioned before, instance methods are called on instances, and static methods are called on either the class or an instance. To call methods and to access properties, we use a thing called dot notation. So in this example, we have student1 dot watch lecture, which means the watch lecture function that is contained within the instance called student1. You can also, for instance, access student1's grades by doing student1 dot grade, which will give you access to the variable because it's public. However, calling instance methods on classes will not work and will cause an error. So if I were to say CS61B student dot watch lecture, this would error on compilation because, like I said before, it doesn't really make sense to the concept of CS61B student as a concept watching lecture. However, updating grades can be called on the class. It can also be called on an individual instance. This does the exact same thing as the line above it. Now that we've covered that, we can move on. Just to recap, that static variables and functions belong to the whole class. Every 61B student shares a professor, and if Professor Hug were to take a long vacation and get replaced for a while, then every student's professor would get replaced at the same time. Instance variables and functions, however, belong to the individual instance of the class. So each 61B student has their own personal ID number, and changing student A's ID number doesn't change anything else for student B. Now that we've covered all of that, we can go on to our worksheet. The way this is going to work is I'll give you guys a couple seconds where you can pause and try to do each problem on your own, and then I'll go over the solution. Okay, so our first problem is our first Java program of the semester. The question is, what does each line do? So take a couple seconds and pause and write down next to each line what it does. Okay, welcome back. So now that you, I hope, at least attempted the problem, let's talk about it. So the first line here, it is declaring a new variable called size, which we can describe in box and pointer diagram like that. Size can only contain integers. Unlike Python, if you've taken 61A, Java is not as flexible with its types. Each variable, once you've declared it, you cannot put anything in it that isn't of the right type. So in this case, you have integers and you cannot put, for instance, a word in here. It'll cause a compiler error. So we have size, and here we're putting in 27. The next thing we're doing is declaring a string called name. We'll talk more about this next week, but name is not a primitive type, it's actually a object, which means that for name, the string Frodo isn't stored in the memory location that name is assigned. Instead, in that memory location, there's a pointer to a different memory location that actually contains the name Frodo. Next we go to this, which is a lot more similar to what we were looking at during our mini lecture. Here we're declaring a variable called myDog. And again, it's a class, so we don't just put the dog in the spot. It contains a pointer to where the dog is. Don't worry too much about that. We'll go over it next week. But we're making a box that only a dog can fit in, nothing else. And we are creating a new dog by calling the dog constructor with the name and size that we have above. So we have a dog object with the name being Frodo and the size being 27. Now we can go on to the next line. Here we have int x, which is again a new variable, and it's an integer, so we can just plop it right in there. Is size minus 5. So our computer goes up, checks the value of size, which is 27, subtracts 5, and puts that value here. Now we see our first real block. So the first thing we do for an if statement is look inside the parentheses and see whether or not the condition is true. In this case, x is less than 15. Is it? Well, we know that x is 22, which means it's not true. So that is false. If the block of code is false, you don't even have to look inside to see what happens because nothing happens. It doesn't even, this line of code is not evaluated at all. We just completely skip it. So now we can go to our next block, which is while x is greater than 3. X again is 22, so it is greater than 3. So what's happening inside here? Well, the first line subtracts 1 from x each time it runs, and the second line calls myDog.play. So each time this while loop runs, we're subtracting 1 from x. So x goes from 22 to 21 to 20, etc., until it is no longer greater than 3, which means it happens a total, so eventually x will become equal to 3, and the while loop will evaluate as false and we can move on. This means that myDog.play happens a total of 19 times because 22 minus 3 is 19. Moving on, the next block of code right here is instantiating an array, an integer array specifically. Like strings and dogs, arrays are objects, not primitive types, so it points to where the list is in memory. Put it underneath because I ran out of room. Like that. And then we move on. Ooh, our first print statement. So we can pretend there's been a console here. And so system.out.print hello. All that does is print out the word hello with a space after it. Doesn't do anything else. The next line does system.out.print line dog plus name. So one thing to note here is the difference between print and print line. Print just prints whatever and doesn't do anything else after. Print ln or print line prints out what is expected, so hello dog Frodo, and then it basically hits enter. So next time you print anything, it'll be on the next line of the console. So here we have system.out.println numList1. So we go back to our array and figure out, okay, the 0th item is 2, so the first item is 4, and we print that out. And again, we have println, so we hit enter afterward. And then we have if numList3 equals 8, something happens. So again, we'll go back to our array. The 0th item is 2, the first item is 4, the second item is 6, and the third item is 8. So this evaluates as true, which causes our computer to print out what it says in the next line, which is potato. And just like that, we've reached the end of our first Java program. Now, let's move on to something a little more complicated. Here you're given a function called mystery, which you don't know what it does. And let's figure out what we can tell about it. So the first question is, what would mystery return if we set input array to equal 3, 0, 4, 6, 3, and k to equal 2? I'll give you a couple seconds to think about it. Welcome back. So let's step through together with these parameters and see what happens. So first we pass in input array, which gives us 3, 0, 4, 6, 3, and k, which is just 2. Now the first thing we do is we declare a new variable called x, and we set it to be equal to input array k, which means we go into input array, we say 0, 1, 2, we take that value and put it in x. Now we do int answer equals k, which just means that answer is also equal to 2 now, and index is equal to k plus 1, 3. Now that we've done all of that, we can enter the more interesting bit, which is this while loop. Now, what is the condition? So input array.length is equal to 5. So what it's checking is whether or not our index is less than that. And since our index right now is 3, it is. So we can move on. If, So the next condition is if input array index is less than x, then whatever after that happens. So we look at input array index, which is the third item in the array. So 0, 1, 2, 3. Input array index is 6, and x is equal to 4. Is 6 less than 4? No, of course not. So we can just ignore everything that happens after this if statement. And all that happens in this loop is that index gets iterated by 1, and index is equal to 4 now. So now that we've done that, all we do is we iterate index to 4, and we go back to the top and we check the condition again. Is index still less than 5? And since 4 is less than 5, the answer is yes, and we evaluate what's inside the loop again. So now we check the if condition again. If input array index is less than x, then we evaluate the code block. So again, we do 0, 1, 2, 3, 4, and this time input array index is 3, and x is equal to 4, and since 3 is less than 4, we evaluate the code block. The first thing we do is we set x to be equal to the new smallest value, which is 3, and then we set answer to be equal to the index, which is 4. And then we iterate the index one more time, and then we go all the way back up and check our while condition again. This time, our index is 5, and 5 is not less than 5, which means our while condition evaluates as false, and we can escape that whole code block. So now we are here at return answer, and answer is equal to, oops, I think I switched K instead of answer. There we go. So answer is equal to 4, and we can return that. Now, based off of what we just did, can you explain in English what mystery does? I'll give you a couple seconds to think about it. Okay, so I hope you've thought about it, and I hope you've written something down. Based off of what we see, what mystery does is it finds the index of the smallest element that occurs at or after index k in the array. So the first two items are completely ignored because k is equal to 2. So we only care about what happens after this line. And so the smallest item was 3, right? Which is why we return 4, because that is the index of the smallest item. The variable x keeps track of the value of the smallest item so that we can do comparisons. And then the variable answer keeps track of the actual index of the item so that we can return it at the end. Now that we've done that, we can move on to a slightly harder problem. This is an extra problem, so don't worry about it if it's a little difficult, because it's meant to be. For this problem, I want to describe what mystery 2 would do if we gave it the same input array we gave the previous problem, which is 3, 0, 4, 6, 3. I'll give you a couple seconds to think about it. Okay, I hope you've given it some thought and written something down. Let's draw out our array a little bit bigger because we're going to be doing some manipulation today here. Okay, so the first thing we do is set index to 0 right here, and now we immediately enter a while loop. And again, the input array.length is 5, so we can just keep them there so we remember. And we're checking, is the index less than the length of the input array? And of course, right now that's true, so we move in to evaluate the contents of the code block. And the first thing we do is we run mystery on input array comma index. In this case, index is 0. So essentially, we're running mystery on the entire array. And what does mystery do? It returns the index of the smallest number after this point in the array. So looking at our array, which index is it going to return? It's going to return the index of 0, which is 1, because it is the smallest. So I can write that down here. So we have our target index, and what we do in these 3 lines is essentially we're going to swap the values of the value of the array at the current index with the value of the array at the target index. So we set temp to be equal to 0, so we don't lose it when we swap it. Then we set input array at the target index to be equal to input array at index, which means that this is going to be set to 3. And good thing we made that temp variable so we don't lose the 0. We set input array at index to be equal to temp, which is 0. And then we increment the index. And then we go through this again. The while condition is still true because 1 is less than 5. We find the target index. So remember, k is now equal to 1 right here, which means we're not going to really look at anything before this in mystery. So now the index of the smallest value is actually still 1. So what happens is we set temp to be equal to 3, and then we basically swap it with itself, which does absolutely nothing. And again, we increment index to 2, and then we move the bar over a little bit, And our target index return this time is 4. This is, if you notice, this is the same thing that we actually ran when we did mystery the first time. So now it's going to return target index of 4. Our temp value is still 3 because this is the new smallest value. And when we do the swap, we get 3 and then 4. And then we increment the index to be equal to 3. Which moves this little bar over. And then our target index is 4 again because the last number, because 4 is less than 6. But our temp is going to be 4. And then we swap the 2, which gives us 4 and 6. And then we run through it one more time with index of 4. Except this time when we go into mystery, we don't even run this loop because index is equal to k plus 5 here, which would mean it's already too big to ever even go in. So it immediately just returns 4 and nothing changes. And that's all mystery 2 does. This is actually called selection sort, which we will learn later in the class when we go over sorting algorithms. Don't worry about that. All you have to know is how to analyze a function like this and see what it does. Okay, we've been analyzing so many functions. Let's finally get to write our own function. So the first thing we're going to do today is implement the Fibonacci sequence. So just for a quick refresher, the Fibonacci sequence says that f of n is equal to f of n minus 1 plus f of n minus 2. That means the sequence essentially looks like 0, 1, 1, 2, 3, 5, 8, 13, and on like that. We're going to do this recursively because even though recursion is scary, it's actually the easier way to do this. So, first, there are a couple questions to consider. What's the base case? And then, what's the recursive call? So for the base case, let's think about it. At what point can you do no more calculations to figure out what the Fibonacci number is? Well, how about we just start with the first number, right? Because there's no Fibonacci numbers less than 0. 0 is the first Fibonacci number, which means once you've hit 0, there's nothing more you can calculate. 0 is just happens to be the first number. There's nothing else you can do about that. So perhaps that's the base case. We can just say if n is equal to 0, because we're looking for the 0th item, then we return 0. Okay, that's great. Except, let's say if I wanted the second item, right? So I want f2, which should be equal to f1 plus f0. And I have f0, right? I have that base case. But what's f1? There's no negative first Fibonacci number, so how am I supposed to calculate that? The answer is you don't. There's actually 2 base cases for the Fibonacci sequence. So you do else if n is equal to 1, if you're looking for the first Fibonacci number, then you can return 1. There are more condensed ways to write this, but this works too. Okay, so that's our base case. We've solved that problem. Now, what is the recursive call? Well, lucky for you, the Fibonacci sequence is pretty fun because it's actually recursive already. You don't have to think too hard to figure out how to write this recursively. If our function is fib n, then technically fib n should be equivalent to just writing fib n minus 1 plus fib n minus 2, right? That's the same thing. And that's exactly what we're going to do. We're just going to return fib n minus 1 plus fib n minus 2. Now, if you're wondering how we can prove that this works for all of the Fibonacci numbers, the answer is you don't have to prove that it works for all the Fibonacci numbers. You just have to prove that it would work for any arbitrary Fibonacci number. Let's say I pick 5. So I want fib 5 to return the right value. And I'm going to assume that every number below 5, every fib n where n is less than 5 already returns the correct value for sure, that I already know this information. So based off of that, I know that fib 5 is the same thing as calling fib 4 plus fib 3, and that's what's being called. And since I assume that fib 4 and fib 3 are already returning the correct values, I know that fib 5 will also return the correct values. This is called the recursive leap of faith. It assumes that if some kth iteration of this function works, if on the condition that all of the previous ones work, then you can prove that every iteration will work. Okay, now that we've done this, let's get to our last problem. Now this problem's a little tricky, so don't worry if you're completely lost at first, because trust me, most people are. I'll give you a couple seconds to think about it, but the goal here is to implement Fibonacci 2 recursively in 5 lines or fewer using these variables. Okay, welcome back. I hope you've got something written down. Don't worry if it's not right, we're going to go over it right now. So, before we try doing anything recursively, let's just try doing this iteratively, right? So if you have the Fibonacci sequence, right, you have f n equals f n minus 1 plus f n minus 2. And the way we did it before was we basically, calculated each of these separately and then calculated all of those individual components separately and on in this big tree. But the issue with that is that's a big tree for even a relatively small Fibonacci number. And there's a lot of duplicates among the branches. Like if fn minus 1 is just equal to fn minus 2 plus fn minus 3. So already we're calculating this twice in its entirety, which will take a lot of processing power. So our goal is to do this a lot more efficiently. Now, we know that fn minus 2 plus fn minus 3 is equal to fn minus 1. But we also already just have fn minus 2 for doing this. So why can't we just also return that? And that way we don't have to recalculate fn minus 2. And then you're wondering, how do we get fn minus 2 in the first place, and how do we get fn minus 3? Well, we can just do fn minus 3 plus fn minus 2, or fn minus 4 is equal to fn minus 2, right? So again, we can just get the fn minus 2 and fn minus 3 at the same time. So we're going to do this iteratively, ignoring everything else. We could do, int n is equal to n, whatever value we're trying to get to, right? Whichever n Fibonacci number we're trying to achieve. Int k, let's start off at 0. Int k will go up every time, and when k equals n, then that means we're done, because that means we've done it k times. Now we have f0 and f1. So what are the absolute base cases that we talked about before? 0 and 1. There is no way to calculate those. So we can start off with 0 and 1. Eventually, if you keep going down this line for a very long time, you will end up with 0 and 1, which is what our goal is here. Our goal is to start from here and go up k times. So we'll create a while loop while n is not equal to k, or you can also write while k is less than n. Those will achieve the same thing. So let's see, in every iteration, let's say this column is the f1 and this column is the f0. Let me fix this bottom part to fall in line with that. Okay, right? So what we know is each f0 is equal to the f1 from the previous iteration. And each f1 is equal to the sum of f1 and f0 from the previous iteration. This is almost perfect, except for the fact that when we assign f1 to f0, we lose the old value of f1 we have. So what we have to do first is create a temp value, like we saw in mystery, which holds the value f0 from before. That way we can do the sum efficiently. Okay, that's all. So we keep doing that. We'll keep climbing this ladder. We also have to iterate k each time. And then when k is equal to n, then we're done. We exit out. But what do we return? Do we return f1 or f0? Well, on the kth iteration, which one is correct? Well, let's try some simple base cases, right? So if we're looking for the 0th number, if we're looking for the 0th Fibonacci number, which is 0, then n is equal to 0, k is equal to 0. That means we never even do anything in this while loop. So what we would want is to return f0. If we're trying to do the first Fibonacci number, then n is equal to 1 and k is equal to 0. So in this case, we will have swapped the f1 and f0 at this point, so we would want f0 again to be returned. And if you can try a couple more numbers if you're still unsure, but the answer is you want to return f0. This is great. We have what we want, except it's iterative and it's a lot longer than 5 lines. And we're not really using the fact that all these variables are passing in as parameters, right? So let's take what we have right now, put it to the side so that we can still see it and reference it, and try figuring out how it is recursively. So, to answer the first question, what is the base case? You can think of the base case in recursion as basically the opposite of this condition in iteration. Because in recursion, the base case tells you when the base case is true, you stop recursing. Similarly, in a while loop, when the condition is false, you stop iterating. So what this means is our base case is going to be the opposite of this condition, which is instead of n is not equal to k, we say if n is equal to k, then we stop doing any more recursive calls. And what do we return? Well, we return f0, like we figured out before. Okay, that's great. But that's the easy part, right? So what do we return otherwise? So let's see. Let's go through each of these variables. First of all, we know that the n doesn't change throughout this whole thing. N is just there so that we know which iteration we're on. So that doesn't change. K, on the other hand, increases by 1 every iteration, right? So we should probably do k plus 1. f0 is actually going to be equal to f1. So for f0, we're going to pass in just f1 straight up. And then for f1, we're going to pass in the sum of f0 plus f1. And if you look closely, you can see that this recursive algorithm is doing the exact same thing as that iterative algorithm. Now we have a much more compact and efficient way of calculating the nth Fibonacci number. So that wraps up our worksheet. If you have any questions on anything, there is a discussions tab on Ed. Please feel free to ask questions. I'm sure if you have a question, a bunch of other students do too. You can even ask it anonymously if you're shy. But I hope you all tune in next week /go discussion and have a lovely first week of school.